Hi everyone, welcome to Taylor Polynomials Day 2. Alright, so we are just going to continue with what we left off yesterday. And so now we have a general definition of our nth degree Taylor polynomial, okay, however big I want it. And this at the end right here with all the n's is what we call our general term. Right, so if a problem ever asks you for the general term, it's going to ask it in terms of n. Right, so if, like for any n. Right, and same thing here for Maclaurin. Okay, it's just you plug in 0. Okay, it's the same thing. Okay, now a big deal is the error. Right, so the whole reason why we're using Taylor polynomials is to approximate a function. We're using it to approximate something that's difficult to work with. And the only time that an approximation is useful is if we can figure out what the error is. And the nice thing is that it's a similar in thought to what we did with series. Okay, it's the next term. Okay, it's the n plus 1th term. Right. So if you take your Taylor polynomial out to n, then the n plus 1th term or the next term is going to be your error. Right, and what that does for us is it actually gives us our maximum error. Okay, just like with series, it gives us our maximum error, which gives us a bound. Okay, so it kind of bounds our error, and we can use that to bound our actual answer. So we can figure out, between this value and that value, where is my answer? All right, so we're going to go more into depth about that later. Okay, let's work out a couple things here. All right, so I'm given that a second degree Taylor polynomial is equal to this. So this is just the standard form of a parabola, or general form. And it's centered about x equals 0. Okay, it's asking for the specific signs of a, b, and c if this graph corresponds to my secondary Taylor polynomial. All right, so here's some things that I notice. I noticed that, okay, a second degree Taylor polynomial will look something like this. 0 times x plus f double prime of 0 over 2 times x squared. Okay, so here is my second degree Taylor polynomial centered at 0, which is why I plugged in 0. Okay. And if you correlate this, okay, so if you look here at my constants, okay, they all match up. Right, so f of 0 is actually going to be my a value, f prime of 0 is going to be my b value, and f double prime of 0 over 2 factorial is going to be my c value. All right, those are all going to line up. All right, so here's what I notice. I notice that my y-intercept is way up here. This is my y-intercept, or my a value. Okay, because that constant at the end of your function always gives you your y-intercept. Okay, I see that this is an increasing function, which means, my first derivative is positive, and it is concave down, which means that my second derivative is negative. Okay, so I know that f of 0, which is a, is greater than 0. It's positive because my y-intercept is above the x-axis. Okay, furthermore, I know that f prime of 0, which is my b value, is also positive because my function is increasing. And last but not least, f double prime of 0, which is c, is less than 0. It's negative because my function is concave down. All right, these are all the things that I know. So this is kind of a flashback to our analysis of graphs from last semester, but still useful. All right, let's keep going. Okay, now they give us a third degree Taylor polynomial approximated at x equals 4. They want us to actually find what f of 4, f prime of 4, and so on, what they actually are, what they gave us our polynomial to start with. All right, so I'm going to write down the general formula for a Taylor polynomial centered at 4, just to remind myself what I'm dealing with. Okay, that should be a 2. Over 2, x minus 4 squared plus f 1, 2, 3 over 3 factorial x minus 4 cubed. Okay, so this is what I'm dealing with, and now I'm just going to compare my kind of my general formula here to what they gave me. Okay, well, right off the bat, I know my constant is 2, so f of 4 equals 2. F prime of 4, well, I don't have anything to the first power here, so it looks like f prime of 4 is 0, right, because that term just totally went away, right, so that has to be 0. Now, f prime of 4 divided by 2 is equal to negative 5, right, so I know f double prime of 4 over 2 is equal to negative 5, and I'm just trying to solve for f double prime of 4, so that's going to be negative 10. Okay, and then last one. So same thought, f triple prime of 4 divided by 3 factorial is equal to 8, so I know this is going to be equal to 8 times 3 factorial, which is 48. 3 factorial is 6. Okay. Then part B asks if we have a local maximum, a local minimum, or neither at x equals 4. Right, so judging from what we know, I need to have a critical point at 4. Right, so that means that my first derivative either needs to be undefined or 0. So I'm going to go ahead and write that out. So I know f must have a critical point or a critical number at x equals 4, meaning that f prime of 4 equals 0 or does not exist. Well, that's definitely true. F prime of 4 is 0. Right, so I know that since f prime of 4 equals 0, and let's take a look at our second derivative. It looks like my second derivative is negative. F double prime of 4 is equal to negative 10, which is less than 0, which is negative. That means that my graph is going to look something like this. Okay, I'm concave down, which means that f has a local max at x equals 4. Bonus points if you can remember what that test is called. I'll give you 2 seconds to write it down. 1, 2. It is the second derivative test. Okay, so that was the second derivative test that we just used. So our first derivative had to be 0 or undefined, and then the sign of our second derivative tells us whether we have a maximum, a minimum, or sometimes it can fail. All right, let's keep going. Okay, last one for today. We are given a function again, so we're given a bunch of values here, and they want us to write out the third degree polynomial. Easy enough. So I need to do p sub 3. All right, so my constant goes first, negative 4. Then 2, I'm centered at x equals 3, so x minus 3. Then 7 over 2 factorial, x minus 3 squared, and then minus 5 over 3 factorial, x minus 3 cubed. All right, so easy enough. Then they want me to write the fourth degree Taylor polynomial for this business right here. All right, so now I'm doing a composite function. Okay, I'm plugging this in for x. So let's see what happens. Okay, if I want to write out my Taylor polynomial, well, if I'm plugging x squared plus 3 in for x. So I have no x's here, so that's not going to change. Now I'm plugging x squared plus 3 in for x. Again, I'm plugging x squared plus 3 in for x. I'm actually going to stop there. I'm not even going to plug it into my last term, and I'll show you why. So when I simplify this, 3 minus 3 is 0. 3 minus 3 is 0. now I'm left with a fourth degree Taylor polynomial centered at 0. So I have x minus 0 in each of these. And I have gone up to the fourth power, which means this is a fourth degree Taylor polynomial. Right, so that one worked itself out. So with a little bit of foresight, you can just know kind of when to stop for those. Right, I will see you all later.